Okay, so today we're going to be doing a quick overview of this concept we call ideal flow. All right, and this is something that it's not on the exam. You don't have homework on it. Okay, so it's a little bit of a freebie for you guys. But the idea here is to give you some exposure to ideal flow because it's something that gets used a lot in any fluids courses that you take later on, and that's actually probably one of my favorite topics. But before we get into that, we came up a little short on time in the last lecture, so I wanted to go over one more solution to the Navier-Stokes equations. So I want you to consider a problem where you've got a planar incline, or a sort of a ramp, okay, that's got a sheet of water flowing down it that has a constant depth of h. All right, so the water here is being pulled down the ramp by its own weight, by gravity. We would assume that there's no pressure gradient along the direction of flow, and this is very similar to one of the example problems that I uploaded to Icon. The one difference being that we've also got a breeze that blows parallel to the surface of the water, okay, and exerts a shearing stress on the surface of the water. So how would we go about solving for, in this case, the velocity of the fluid if this is u, right? How would we solve for the distribution of velocities across the thickness of the water sheet? So this is going to be a really abbreviated solution. We can actually do it in really just a few lines. But remember, our first step is listing our governing equations. Okay. First of which is going to be continuity. We're going to go ahead and make the assumption right up front that this is a two-dimensional flow, so we're going to drop everything in the z direction because we saw in the previous examples we did that the z direction disappears entirely anyway. Sorry, this should be dx plus dv dy is equal to 0. Okay, so there's continuity. Then we're going to write the Navier-Stokes equation for momentum in the x direction. We're dropping z entirely, like I said, and we're not going to end up needing y. U dx plus v du dy to negative p dx plus rho x plus mu okay, so this is the Navier-Stokes equation for momentum in the x direction. The reason we've written the equation for only the x momentum is what we're looking for, u. Okay. In general, I would write the x component, the y component, if it's a three-dimensional flow, also the z component. But to speed things up in this problem, we would find that everything in the y component cancels out. Okay. So step 2, list assumptions. Those being, first, we're going to assume that it is steady. We're going to assume that flow occurs parallel to the ramp. In other words, that v is equal to 0. Okay.
And then
we can make an assumption here as well that we could show it more rigorously, but the fact that the water is exposed to the air, right? It's a free surface on top. This means that everywhere on the top of this sheet of water, the pressure is atmospheric. Okay. And so if the pressure is atmospheric, everywhere on top along the x direction, that means that it's going to be, it's constant. There's no pressure gradient at the top. And if there's no pressure gradient at the top, then we can say that there shouldn't be any pressure gradient down lower either. So that allows us to kill off that term. So we can write no pressure gradient dp dx. We'll number these 1, 2, 3, and then we can go through and start canceling out our terms. So that guy goes away, goes 1. If v is equal to 0, that means that guy is 0. That guy is 0. No pressure gradient. That goes to 0. The continuity equation then simplifies to du dx equal to 0, which, remember we said means that is what we call fully developed flow. We'll go ahead and assign that a star, because then we can use that to cancel out this term and to cancel out this term. So we've already kind of executed step 3 there, which is simplify equations. But what we essentially get is then du dx equal to 0. Let me rewrite that a little better. Du dx is equal to 0, and rho gx plus mu b squared u dy squared is equal to 0. Okay, if we look back up here, right, g is acting down vertically, right, which means that gx can be written as g sine of theta. That is because this is g, here's gy, and here's gx. Right? So the direction of gravity acting parallel to the ramp in the direction that the block is sliding. So we'll go ahead and write now that mu b squared u dy squared is equal to negative rho gx. We can move we move the mu over here and integrate twice. Then what we'll end up with is u as a function of y, and as negative g sine theta. Oh, say negative rho g sine theta. 2 mu y squared plus c1 y plus c2. Okay, so this is just this so far has just been pretty straightforward. This part's pretty straightforward math. Part above it requires a little bit more intuition and thought about what terms you can cancel out. But now is where we start to identify what our boundary conditions are. So we're not going to take this problem all the way through to completion, but I wanted to say, once again, we have 2 unknown constants of integration. So what are the 2 boundary conditions that we could use to find those? So let me go ahead and bring this, copy this, bring it down here. Okay. So if we're looking at this flow here, anyone want to volunteer at first boundary condition? What can we say about the x component of fluid velocity? Notice, by the way, I didn't point it out explicitly, but our coordinate system, we tilted so that x is pointing down the ramp. How about at the surface of the ramp? Here's some whispered zeros. You can be braver about it. Yes, it's 0. It's up against a surface, so the velocity has to match the velocity of the surface. If that surface is fixed, the fluid has to remain fixed as well. And so we can say u equals 0 at y equals 0, right? So that's boundary condition number 1. Boundary condition number 2. This one's a little bit trickier. Any thoughts? So there's a clue right here, right? We've been told that there's a breeze blowing past the surface of the water, okay, and it exerts a shear stress. How do you write the shear stress based on the velocity? Right? So what we would write here is that mu du dy is equal to this externally imposed shear stress at y equals h. Okay. And so if we take du dy, this ends up being negative g sine theta, or negative rho g sine theta over mu y plus c1, right? If we had integrated this one time, or if we took the first derivative of this term to get the slope. And so this tells us then that negative rho g sine theta over mu times h plus C1 is equal to, right, whatever the shear stress tau is. And so using that, we're able to solve for C1 using the first boundary condition, right? This gives us the C2 is equal to 0. And so now we've fully defined our unknown constants of integration. If this process seems, if this isn't clicking, or if this isn't making much sense, I really do suggest taking a look at the examples that I put up on Icon, because I try to annotate those pretty thoroughly to explain each step, and they're written out in more detail than this one. But this is this is another one of those very few problems that we can actually fully solve the Navier-Stokes equations for, because if we plug in our values of C1 and C2, we end up uy equal to rho g sine theta over mu h y minus y squared over 2 plus tau over mu x. Okay. Any questions on this?
Where'd you get the X?
Sorry, that should be a y. My bad. That's a y. I had it written down as an x because, yeah, transcription error. All right. Okay, so kind of main event today. is sort of a bird's eye view of this section of chapter 6 that we skipped entirely in this class. I don't want to leave it totally untouched, but the idea is not to make you do any hard math or make any problems, but simply show you what can be done if we use certain simplifications in the way we approach flows. So we've talked about Navier-Stokes, right? This is sort of the full bore, the all-in equations of motion. That includes viscosity. It includes shear stress, rotation, right? It'll describe any flow that is Newtonian, incompressible, and continuous. All right. But there are certain assumptions that allow us to make use of some really clever, kind of elegant theories. These tended to come about in about the 1800s, early 1900s. And the two that we're going to talk about briefly today are this assumption of incompressible, steady, and two-dimensional flow, okay, which leads us to this thing that we call a stream function, given by the Greek symbol psi, and irrotational flow, okay, which leads us to what we call a potential function, given by Greek symbol phi. So we're going to start off with stream functions. And the idea with a stream function is that, let me fix this. There we go. The idea with a stream function is that it's defined for these flows in which we can make these three assumptions. That the flow is steady state, that it is incompressible, and that it is in two dimensions only. Okay, so taken together, right? Steady means that all time derivatives go to 0. Incompressible, right, means that the material derivative of density goes to 0. And 2D means that x and y fully define our space of interest. Okay. So, written in 2 dimensions for an incompressible flow, the continuity equation, and conservation of mass, is written like this. Right? This is simply our expression of grad dot v is equal to 0. Okay. So we define this hypothetical function, psi, which is a function of x and y, and we say let's let the velocities u and v be defined by the partial derivatives of this function. U being the partial psi partial y, and v being negative partial psi partial x. Right? This is very intentional because the idea is, now if we were to plug these two definitions of velocities into the continuity equation right here, what we would end up with is, right, du dx is equal to, right, d squared psi dx dy, dv dy is equal to d squared negative d squared psi dx dy, right? So du dx plus dv dy, our continuity equation, can end up being d squared psi dx dy minus d squared psi dx dy, which is always going to be 0. So the point here is that any time you define a velocity field based on some function, using these expressions, that velocity field will satisfy conservation of mass. Okay. Now what's the advantage of this? Well, really just one, and that's that if we were given a flow and we were told, find u and v, we've got 2 unknowns. Right? If we say, find a stream function that defines u and v, we have 1 unknown. So this is simply, this is a tool that we use to simplify the number of unknowns we have in a flow. Other things, so given in cylindrical coordinates, we have the continuity equation, right? written on the top. And then we have definitions for the radial and angular velocity, also as a function of psi. So this can be defined as either a function of xy or a function of r theta. But other useful facts about the stream function. Okay. It's called a stream function for a reason, and that's that when we were talking about fluid kinematics the first time, and we defined this idea of a streamline, we wrote, what's the equation of a streamline? We derived it from this expression right here, where we said that the slope of a streamline is equal to the ratio of its velocities in the vertical and horizontal direction. So by some math here that I'm just going to skip over, what we find is that if we try to track the change in the value of psi, or stream function, moving from one point to another along the streamline, we get that the change is 0. Meaning here is a profound one. It means that lines of constant psi are streamlines. It also means that different streamlines given by different values of psi. So we have a streamline here. We might say that this has a value of psi equals 5, perhaps. Okay. That is, if you have psi as a function of x and y, and you were to make a contour plot, say, show me a line where psi is equal to 5, you might get that line. If you said draw a line where psi equals 6, you might get the next streamline. All right. So this is a really useful tool for plotting out the way that a flow looks. And it has a lot of other uses as well. So here's an example of one being used. Let's say we define a stream function. The psi equals ax squared y minus a y cubed over 3 plus a constant. Okay. A is also a constant here. That we could arbitrarily, tune up and down. But if we defined, then if we use those expressions for velocities, right, that u is equal to d psi, dy, v is equal to negative d psi, dx, what we would get are these expressions for u and v. So what I did here is I plugged this function into MATLAB. I did this last night and said, all right, plot me a vector field. Okay. And what we got was this vector field here, with these blue arrows that show that the flow is sort of moving in these kind of broad looping patterns. I then said create a contour plot of psi. And what I got was these blue streamlines, which you'll see are tangent to the velocity vectors. Okay. So that is there to demonstrate that these lines of constant psi are in fact indicative of the path of flow. So one of the nice things about this, and this is something that I like to point out, is can flow cross a streamline in 2D? No, that's the definition of a streamline, is that flow is always along it. Okay, so you can never have flow moving across it, which means that a streamline can behave as if it's basically a virtual wall or a boundary. And so one trick that people have been doing for about 150 years now is to create a stream function that creates streamlines that look like something that they want to model. Let's say I was interested in modeling the flow through an internal corner. Okay. That sort of 60-degree corner up at the top. If I proposed this stream function and I really just looked at that sextant of the flow up there in the upper right, then what I have is sort of a really simple analytical model that approximates the way that flow moves into and through and recirculates through an internal corner. Okay, so you can do this for a lot of different types of geometries. This is a very simple one, and we'll do one here in a few minutes. once I introduce the Streamlines sibling, or the stream function sibling. So this is our function psi. There's another function that we like to use called the potential function. So the stream function was defined for incompressible flows. If instead, let's get rid of all those assumptions. Okay, we're back to assuming it's a viscous flow, assuming that it's unsteady, it's in 3 dimensionals, etc. If we say, okay, I want to make the assumption instead that the flow is irrotational. Remember that irrotationality means that omega is equal to 1/2 grad cross v, right, is equal to 0. Then I'm going to define a new function, phi. This one is a function of x, y, z, and t. So it's 3 dimensions. It can be unsteady. And I'm going to define the velocities now, similar to the way I did for the stream function with some differences. Now u is d phi dx, v is d phi dy, w is d phi dz. So each velocity is the partial derivative of phi in its own direction. This means we can write the velocity gradient, or the velocity field, using simply grad. Again, the advantage here, instead of having 3 unknowns, u, v, and w, we have simply one unknown function, phi. Rather than going through, so the irrotationality here, we would find that, I'll do it for one example, right? If we're interested in the z component of rotation, right? This is given by 1/2 dv dx minus du dy. And this is something we covered in the beginning of chapter 6. This would be so that is going to be identically 0 all the time. And we find the same thing for the x component of rotation and the y component of rotation. Again, it's just a matter that if we define any function of x, y, z, and t, and we define a velocity field based on that function, it's always going to be an irrotational velocity field. Okay, so I want to put these 2 ideas together. So we've had one that assumed incompressible flow, one that assumed irrotational flow. If we combine these 2, we get what we call ideal flow. So ideal flow means we're going to treat it as if it's inviscid, right? An inviscid flow can also be modeled as an irrotational flow. If we don't have any fluid rotation, we don't have any velocity gradients, means there are no shear stresses, there's no viscosity to worry about. So, right, and then we've got incompressibility. So the idea is we have one function that satisfies each of these. We've got the potential function that satisfies the first. We've got the stream function that satisfies the second. I'm going to focus on the velocity potential. This is the one I think is the more useful of the 2 functions generally. And so we say which of these 2 automatically satisfies irrotationality. The idea there is we have, we've got we've got the potential function phi. If we then said, okay, now we want to impose another condition on phi that says it has to be incompressible. How do we do that? We say it has to satisfy the continuity equation. So grad v, right, or grad dot v, the divergence, turns into grad dot grad phi, because this gives us the velocity field, which turns into this expression right here, this grad squared of the velocity potential. And this has a special name. This is what's known as Laplace's equation. Laplace's equation is really important in not just fluids, but in electromagnetism. Okay, if you get into more advanced physics courses and start talking about voltage potentials, okay, that's where this theory originally came from. Okay, and it was simply co-opted to describe fluids as well. So the Laplace equation, if we expanded it out, it looks like this. in Cartesian coordinates. Okay, simply saying that the sum of all the second derivatives in x, y, and z has to add up to 0. So this is Cartesian. And then if we wanted to write it in cylindrical coordinates, got this. All right, so broad strokes, kind of where do we stand? We've established that there's some kind of function. Okay, it can be whatever you want. You can make up a function off the top of your head, and it can be used to create a velocity field, okay, that will satisfy irrotationality. If we also say that that function has to satisfy this equation right here, then that function can be used to create a velocity field that satisfies these ideal flow assumptions. When is this actually useful, right? This is pretty restrictive assumptions up here. This idea of inviscid flow, incompressible flow. I showed this slide once before, but it turns out that these assumptions end up being useful really a lot of the time. So I mentioned before that whenever you have flow past a solid surface, okay, you have this non-slip boundary condition, which says that you have to the velocity of the fluid and the surface have to match one another. That gives rise to what we call boundary layers, where if the flow is going to go from the surface velocity to the flow velocity, there has to be a gradient between those two values. And if there's a gradient, that means there are going to be viscous shear stresses. Okay. The thing is, though, that gradient region is usually pretty limited. And so if we have the flow really near a solid object, or if we have the flow way at the very end of a pipe or something where the viscosity has had time, the shear stress has had time to affect the entire flow, then that's areas where this ideal flow theory doesn't work. However, huge regions of flow, for example, between the boundary layers in a pipe, or anywhere outside of the boundary layer away from the flow around an airfoil or something, we don't have any appreciable velocity gradients. Okay? And if we're working with a fluid like water or even air at low Mach numbers, we can get away with this idea of incompressible flow. So this means that really, 99% of the fluid that surrounds engineering problems can be described relatively well using ideal flow theory. So the idea of ideal flow theory, now that we've set it up, I only have a couple more slides here, is this. We've got sort of a standard toolbox of what we call potential functions, or velocity potentials that describe very useful types of flows. So, for example, if we take uniform flow, okay, this is just flow in a given direction. We'll limit ourselves to 2 dimensions right now because it makes the math a lot easier. We consider flow just in a particular direction, not curving, not moving, it's just uniform, straight line. We can write a potential function. The phi of u has x cosine alpha, y cosine alpha, where alpha is the angle of the flow relative to the horizon. So that would be this case right here. We have what we call sources, which act like, basically they produce flow outward from them. Okay? And alternatively, we have sinks, which suck flow in toward them. These are what we know as velocity, or as potential singularities, because they actually violate incompressibility right at the center, but because we can play with some mathematical tricks that allow us to ignore the very center and everywhere else that satisfy this idea of incompressible flow. The idea is that a source flow is going to come out very fast, okay, and then it's going to slow down as it radiates outward. So this is similar to a case where if you were to take, for example, like if you were to take one of those soaker-style garden hoses, right, that's porous and allows flow to come outward from it, and if you were to put this between 2 plates and kind of watch the flow, it is that a certain amount of mass per unit second is coming out from that hose radially, and as it expands, or as it moves outward, it has to slow down because it's moving across a greater area, right? The circumference of the circle is growing as it moves away from its source. And so it has to slow down in order to satisfy continuity of mass, or conservation of mass. So we have sources and sinks, which each have, which have the same velocity potential with different signs of m, where m is what we call the source or sink strength. And then we have a vortex. Okay? This is another type of singularity where it satisfies irrotational flow, except at the very middle. And this is a really hard thing for people to get their heads around sometimes, but there's a particular type of vortex that does this. So a vortex like this, the velocity, if we were to plot the velocity across it, let's say the radial the angular velocity, we would find that it looks like this. It starts out small, gets really large, gets really large, gets really large, and then switches sign. Okay? If you ever are able to look at wind speed data that's captured by like a meteorological station as a hurricane passes by, this is what you'll see. This is a really good model of the way that flows behave in naturally occurring vortices. And similar to the source and sink, that is, it violates irrotationality only at the very center, but we can mathematically ignore the very center for a reason I'm about to show you. So we've got these 4 building blocks. Okay. So switch into math mode for a second. If we say that we've got some potential function a, phi a, and some potential function phi b, and they both satisfy this Laplace equation, are we able to say anything about some new potential function we make by summing those two together? Is it also going to satisfy the Laplace equation? Okay. Remember that this is squared. This is what we know as a linear partial differential equation. Okay. The idea with linear differential equations is that if you have individual solutions to them, okay, you can sum those solutions up and they'll still satisfy the differential equation. In this case, if we said phi squared of phi c squared of phi a plus phi b, get this is phi a plus double squared of phi b. Okay, and so if this is equal to 0 and this is equal to 0, because we've verified that both of those individually satisfy the Laplace equation, we say that this is 0. Okay, this is the cornerstone, or this is really the punchline here, is that this says that we can take these building blocks here, because each one of these has been established to satisfy the Laplace equation, and we can essentially take a source, put it here, a sink over here, a vortex here, uniform flow over here, and we can sort of build up a model for flows by adding together those individual functions that we've been given. Okay? And if we do that, we're guaranteed that because each one of them individually satisfies this ideal flow theory, that the sum of all of them will also satisfy the individual flow theory. Case in point, let's see how we would model a spinning baseball. Okay? This is a classic one. So if we take a uniform horizontal velocity, okay, we would write this in polar coordinates as phi equals u times r. This should be, that's right. Phi equals u times r. If we take a source and a sink and we put them at exactly the same spot, okay, we add them together, the math actually simplifies down and we get this expression right here. This is what's known as a doublet. Sometimes it's also presented as another type of classic potential function, but really all it is you put a source right here, and the flow comes out of it and goes right back into a sink that is sitting basically right on top of it. And if we take a vortex, okay, one that has, right, simply streamlines that simply rotate around the center, or go in circles around the center. And if we add all of these functions up, okay, so we'll call this one V1, V2, V3. Then we can write a master potential function that is simply UR plus K cosine theta over R plus gamma over 2 pi V. So we've got really we've got a couple of parameters here that we could tune. So U, right, is going to govern the speed of the flow past our baseball, or our cylinder in this case. This K here is going to define the diameter of our baseball. And gamma here is going to define the rate at which our baseball is spinning. And if we sum them all up, what we get is something that looks like this. Right? So these shown here are streamlines. The dark black streamlines, or sorry, the thick black streamlines are ones where I've said that these are what are known as stagnation streamlines. And so the circular one there, it defines the outside of our baseball, right? And the ones that go in and out of it define the streamlines that would hit this baseball and simply stop, as opposed to going around it, okay? Or simply stagnate against the surface of the baseball. So we've got streamlines going under it, streamlines going over the top of it. And if we were to draw the velocity vectors, I forgot to do that, what we'd find is that they're going in this direction. So if we've got phi, and it's very easy then to write V is equal to grad phi, then we have easy access to the velocities everywhere. And if we know the velocities everywhere, and we assume that it's incompressible, that it's inviscid, then we can use like Bernoulli's equation to draw the pressures everywhere. And if we do that, we get a pressure field that looks like this. Okay. And so if we looked at this, what we would see is, or if we look at this in detail, what we'll see is, we really zoomed in, what we see is that these blue regions right here and here, these are regions where the pressure is relatively low. But if we really zoomed in, we would find that the pressure on the top here is actually a little bit lower than the pressure on the bottom. And if we integrate it around, what we would get is that there's a resultant lift on our baseball. Okay, so this is a mathematical description of what we call the Magnus Effect. And what this says is that the lift on an object is equal to, let's see if I'm writing this, well, I might be transcribing this wrong. I'm going to skip the equation for that right now. But that the lift is proportional to the product of the flow speed and that vortex strength gamma that we defined. Okay. So here's a mathematical description of why a fast ball will track straighter than a ball that doesn't have any backspin, or why a curveball works. It also enables really interesting things if you have time on your hands and you want to see more. Google or go on YouTube and look for things called Magnus Effect flyers. They're basically planes that are made with cylinders that rotate really fast, and if they have a small propeller on the back that moves them forward, then they can rely on this Magnus Effect to generate all the lift that they need to stay aloft. This is an example that I particularly like. It's this YouTube video of dropping a basketball off of an extremely high hydroelectric dam. make us watch some ad. Okay, so these guys have gone up to the top of this 140-meter dam, and they decided that they're going to drop a basketball first without any spin, and then by applying some backspin and seeing if you can observe the effect of this rotation, this Magnus effect. So here's the basketball being dropped with no spin. You see as it gets pushed around a little bit by air currents and such, but it falls basically straight down. Okay. Oh. And here it is with backspin. Okay. And I think they said they measured it and it traveled something like 400 meters horizontally for a 140-meter drop. So this isn't just mathematical witchcraft that allows us to use things like potential flow to model this, or to say that there's lift created by backspin. This is an actual, real, observable phenomenon. And so the idea with this kind of quick tour de force through this idea of ideal flow was not to bombard you with partial differential equations and make you do a bunch of math, but simply to give you an appreciation for the fact that if you make some really well-chosen assumptions about certain things, okay, like the compressibility, irrotationality, you can use these really clever mathematical tools to model real phenomena. So this was something I was able to put together in about 10 minutes in MATLAB. Anyway, so before you guys take off, please note, I hope you all got the email that I sent out yesterday. We decided there was a large group of students that had an unavoidable conflict with the midterm exam on Monday. So we moved the midterm exam to next Friday. I got emails from a few of you saying that you have new conflicts with the Friday time. If you're one of those, I am working on a solution. There will be an alternate time for those that have absences next Friday night. They can't make it to the midterm. There is a practice exam that has been uploaded to Icon. You can find it under the midterm exam 2 prep materials. I'll upload solutions to that soon, and I'll schedule at the beginning of next week another review session similar to the one we had last week. Yeah.
6 a.m. 6:30.